Good day, future alchemists. Today is day 69. We get into the equilibrium unit in earnest. This, of course, is one of the most challenging topics for most students usually. It's also the most important because it actually explains how chemistry works. So typically we'd be going after being able to calculate delta H, using bond energies, reviewing our homework, and then figuring out what equilibrium actually means in terms of chemical reactions, and then being able to use it to predict what will happen in the future. So if you've been complaining and whining about how many remote assignments you have, as chemistry's had it pretty easy, take a look at how many video lessons that I've been making, and that's just a small sample of them. It's pretty easy. You only got to put up with me a couple times a week. I hope that the videos are helping you out. Look, I ended up just below the word rectum. Now, key things, of course, today we need to talk about beep, beep, motor vehicles, right? And one of the things we should notice, of course, this is a combustion vehicle, so it's going to run on fuel, a combustion reaction. And there are many different fuels that we could choose to put in our little slug bugs. One of those fuels, of course, you could put into, say, this sweet-looking Lamborghini, or, a Roadster. Hey, he's got ethanol. What's that? Key thing is I want to know which fuel would work best, because some cars are very picky about what fuel you put them in, and why it would be the best fuel, notice the air quotes, right, for your car. I want you to compare methanol, ethanol, and octane, three that are commonly used, and data is given on this data table right here, so you should be able to use it. Hey, look, delta H. Whoa. Now, the other thing, of course, is you should be able to use claim, evidence, and reasoning to do that, or claim, reasoning, evidence, whichever way you want to look at it. How else could you show it visually? Think back to our last lessons that should help. This is when you should pause me, write down the questions. The only piece of the data that you actually need is the stuff that has to do with these guys right here, right? So home in on that. And then see if you can figure out and explain it just by looking at that data set of what would be the best fuel in your car, especially if you ever filled a car and looked at the pump. Cool. Pause me. Try to figure it out. Come back. Now I'm going straight into it. If we look at this, the key thing I can notice here is I have these three here that are pretty famous. There's octane, methanol, and ethanol, also known as drinking alcohol. If we look at this, the parts that I care about have to do with their chemical formulas and that lovely delta H stuff, because that's kind of nice, and the formulas tell you a lot about how their structure is, right? Now, just looking at the data right there, we can figure out some things. We can figure out some qualitative stuff, because anytime we're doing claim, reasoning, and evidence, we need two pieces of evidence, but we need two types. And qualitative is stuff that you can see or think out, at least, right? Now, this first one is called methanol. And we might as well learn some organic chemistry while we're doing this. Anytime you see meth, such as in the drug meth, it's because they're adding an additional methyl group which has carbon in it. The meth refers to one carbon. The all refers to the fact that it's an alcohol. Being an alcohol, it will have an OH group on it, a hydroxyl group, which you learned as a hydroxide in inorganic chemistry. So the formula for this is CH3, because it's got to have, honk to supply all the bonds for the carbon, and an OH, so that everybody's locked up, has the right number of bonds. If we were to draw that using that, carbon would be at the center of this thing. It would be surrounded by H3. That's a methyl group. And then on the other side of that, of course, would be this thing called a hydroxide or a hydroxyl group. Those tie together and give you this nice bond. And you can see one thing it has in there is inside the molecule, there are bonds, and bonds equal chemical energy. So methanol, of course, is good for, making small fires because it has bonds in it. You can break those bonds and get the energy out. Bigger than that would be something like ethanol. And ethanol has an F, and F means two carbons. We're talking about things like alkanes in organic chemistry. It also has an all, so it's an alcohol. Being that its formula is C2H5OH, the OH tells us it's the alcohol. The C2 is because of the F, and the hydrogens fill in the rest of that. Another way to write it would be its structural formula, which is how I think about it as a biochemist. It's CH3CH2OH. Now, that gives you a better idea what the structure looks like. That's what we call a structural formula. So the center of this, as with most carbon chemistry, is the carbons, because it can make four bonds. Each of those carbons, the first one's got a methyl group. The next one has, of course, the hydrogens attached to it, and then it's got that hydroxyl group attached to it. Now, putting it all together, you can see that this thing, it's got more bonds, and more bonds equals more chemical energy, right? Ooh, that's why alcohol burns so well, and bartenders do fancy tricks with it, or a Molotov cocktail could, take out a tank and stuff like that. Then there's this stuff called octane. And by now you should know that October used to be the 8th month. Now it's the 10th, thanks Julius and Augustus. Because oct, of course, has 8. And that's 8 carbons. And it's known as octane because it's an oil, an alkane. And alkanes are pretty famous. We use them for pretty much everything these days, right? Now, even my screen's made out of them. These are hydrocarbons, which is a nice word for an oil, right? And its formula is C8, because it always tells you the number of carbons that are in it. And then you got to fill in all the rest of it, and it's H18, right? 2n plus 2. Now, key thing that we do with this means that this is carbons, and there are 8 carbons in a long, long chain. And those carbons, of course, have to have 8 of those things. And then all the rest of the bonds to make it honkin' happy. Yeah, I like that, honkin' happy. That's going to be all the hydrogens. And those hydrogens fill in. Of course, they're happy with one bond because honk tells you need one. And as you go through and fill them in and your hand starts to get tired, you're like, hey, organic chemistry is easy. We can see that one thing this thing has a lot more of. It's got more bonds, and it has the most chemical bonds, because by far it does. And it has the most chemical energy. Now, what drives your car forward? That's right, ripping apart those bonds to access the chemical energy. So just looking at the molecule tells you that the best fuel for your car is octane. Well, in terms of an energy perspective, that's why we use octane. That's why, it has an octane rating. That's telling you the percentage of octane on the side of the pump. It also can contain ethanol, but it tends to have 10% in America because ethanol, of course, does supply energy. It's cheaper to make and get than the octane, but it can freeze, so it doesn't work that well at the temperatures. Plus, it doesn't have as many bonds, so it doesn't give you as much energy. Now, that, of course, tells us the thing that we can make a claim about. We can claim that octane would be the best, and I'm putting that in air quotes, oh yeah, fuel for a car. And the obvious reason is because it contains the most chemical bonds, so it has the most chemical energy. Now, you also should be able to do a scientific thing and make that quantitative data, right? Cool, we can actually mathematically prove this. This is where you would make at least 2 mathematical comparisons. And so I'll show you what that means. It just means doing math and comparing the math, like comparing numbers and stuff. And a great way to do that is by using math to make comparisons, like take the differences between things. So a good one would be the example between, say, octane versus methanol. And you can see over this chart, it gives you the heat of combustion. That's the amount of energy that can be produced by this or taken in by it, referenced in terms of these things called kilojoules per mole, which we just did in the last ETD. Now, octane, you can see, comes out at a whopping negative 5,508. We'll just ignore the negative. That just means that it's exothermic. It's coming out, right? And if I take the difference, that's the difference between that and, say, methanol. Methanol comes out at 724. If I look at the difference between those two, it's a whopping 4,784 kilojoules per mole more than methanol. So octane's got a whole lot of juice compared to methanol because it's got more bonds. Then I need a second comparison. Well, I'm going to talk about octane versus ethanol. And look at that. It's still the 5508. A whopping amount. It's one of the most energy-dense molecules that we know of. That's why we run our society on it, unfortunately. And ethanol is right here. It's at, well, it's got more. It's 1368. It's like almost twice as much as methanol because it's got more bonds in it. If I take the difference, I can get this thing called 4,140 kilojoules per mole. And that is how much more than ethanol that octane has. It has that much more energy than ethanol. Notice the words I'm using here is more than. That's the comparison. And I did some math. That's the mathematical comparison part. And I did 2 different pieces of sets of it. That tells you that in a pile of octane, it has the highest energy density of all these fuels. Plus, it's nice and portable. It stays in liquid form until you, of course, reach it to a little bit higher temperature, like room temperature. Then it'll vaporize in your engine so you can explode it, which means it mixes well with oxygen, right? Now, that's why it's the best energetic fuel for your car. It's also why it's one of the worst things for our planet. If you were to burn methanol, what you get out is exactly 1 CO2 because it's got 1 carbon coming in. That'll warm up the earth a bit. If you burn ethanol, like all of Brazil does, because they get from sugarcane, that's 2 CO2s every time you burn it. Ooh, that starts to add up and warm things up. Now imagine if we used octane. Oh, wait, we do. That's 8 times the amount of CO2 it would produce. So yeah, you get a lot of energy out of it, but you also get a lot of smoke. And it's the smoke, unfortunately, that traps the heat on Earth and could, cause the whole climate to shift and our demise. Oh, not this has anything to do with real life. It's just chemistry. That, of course, is a pretty big deal. It's not necessarily the best fuel in terms of keeping us alive because it causes the greenhouse effect to accelerate, as we're seeing in the oceans and the Earth. But it is the best fuel in terms of energy, which is why we're not going to give it up until we find a better fuel source to supply us the energy and not make the waste. Fortunately, some people have figured that stuff out, right? Another way that we can think about this stuff is we can think about this in terms of energy. And the best way to think about energy is energy diagrams. If we looked at the energy diagrams for each of these reactions, because it's a good way to compare them on a reaction coordinate, we could see something like methanol. Methanol has a few bonds, so it's got some height on this tower. There's methanol right there. As you burn it in your car, you break it, you give it activation energy. That's why you have spark plugs. That, of course, bumps it up, and then it makes smoke. And the CO2 and the water are low energy, so the extra heat energy comes out of this thing. That gives you a negative delta H. It's exothermic. That's what drives your car, because that expansion drives the piston, which then turns the wheels forward, right? Unfortunately, most of it turns into heat. So methanol, of course, gives you a little bit of heat, which gives you a little bit of forward motion. Then we could also look at ethanol. Well, ethanol is a little higher on the scale because it's got more bonds, so it'd be a little higher up the hill. And when I jump it, it ends up in the same place because I'm going downhill to make the water and the CO2, the smoke. When I do that, I also end up with a negative delta H, but it's a bigger delta H. It's almost twice as much because, of course, it's got almost twice as many bonds, right? That, of course, allows me to capture that, use that to drive my pistons as well. If I look at octane, octane is like way up here. There's octane. That's why we use it. It also, of course, is very easy to ignite. And when it's easy to ignite, that means our spark plugs can do the magic, but it still ends up at the same place at the bottom. It still makes the same smoke because they're all combustion reactions. Now that gives you a much greater change in the energy of your reactants and your products. That's a bigger delta H drop. So one thing we can see is all these graphs show what's called a net energy exchange. The energy from the reactants going to the products, and these are all downhill battles. And being downhill battles, they give us energy. So energy diagrams do a beautiful thing for us. They get rid of that boring math stuff, and they basically show the energy that's released versus the energy that's being stored. And if we look at this, it's energy being released from chemical bonds that you're breaking. So you're going to have energy diagrams in your next S. Versus the energy that's stored in the bonds, in chemical bonds. And of course, if you make less energetic bonds or less bonds in general, then the excess has to go somewhere, and that's the heat that comes out, right? So if you just simply take the difference like we did last class in our ETD, you get the net energy exchange. And for all of these, it's a negative delta H because it went downhill, and that's measured in kilojoules per mole, so we can compare the amount of energy to the amount of stuff, the pile that's there. And with octane, it's got a big old pile of energy trapped inside a mole of it. That's why we use it, because unfortunately, it's the best portable source for energy in terms of its density jammed into that thing, right? So energy diagrams, a great way to show that. Of course, the opposite of a downhill battle is an uphill battle, right? Then you should also recognize, hey, I made smoke. Can I turn that back into octane or methanol? Well, that's exactly what happens when we do photosynthesis, and that's how corn could make fuel. But that's why I bring up this, and that truck had that funny shape. Lamborghinis and things like that, sports cars need high octane. You got to pay for the expensive fuel because it has a higher concentration of octane, more bonds to get it going. It won't drive on the cheap gas. If you look at these things right here, we can now produce ethanol and methanol from things like corn, mainly ethanol, by using bacteria or yeast to take it, ferment it, and turn the sugars that are in it into methanol and make a fuel. It just doesn't work so great in America because it gets freezing at things like the wintertime. Would work okay for the rest of the year if the oil companies wanted us to do that. In addition to that, of course, here's a different car. It can not only run on ethanol, but it also has a hybrid engine. So it runs on battery power, because the best thing of all of this is the downhill battle that's called a battery is exactly what a battery is doing inside of a Tesla as it drops from lithium, an high energy position, to a lower energy position. Everything, of course, that gets you energy is a downhill battle. And the beauty of this is this thing does not make a bunch of CO2 that could kill us. Hey, look, that's my wife's car. Hey, a hybrid does a better job of, mitigating those downhill battles. Waiting for the day my students buy me a Tesla. It'll be awesome. Maybe after I make 10 million videos. Ha, ha, ha. Now, normally we'd be going after the make it or break it worksheet. I reviewed the big ideas of that last time with the looking at burning methanol and the calculation of the net energy exchange. At this point, we would then go after one of the coolest reactions that I have ever seen and would show you normally. But today, I'm going to have to show you with a video link. That's the yellow-blue switcheroo. And at first, I want you to watch it. It doesn't actually explain how it works, which is the beauty of it, because I wouldn't explain it to you at this point either. And your job is to do this. Our unit is called equilibrium. I want to know what's going on in the beaker that displays equilibrium. Also, it's a chemical reaction. Why is it a chemical reaction? How do we know? And then what actually is equilibrium? So watch the video clip, and you'll see that it's pretty weird. It's even weirder when you're in person because it's the yellow-blue switcheroo. I wish I could show you in person. Think about why it's called the clock reaction as well, because that will introduce us to actually how chemical reactions work in reality, which we haven't got to discuss yet this year. After you've done that, you're going to want to go and check out this link for the PhET Reaction Rates Lab. And it's one of the coolest ones. What you want to do is you want to go into the single collisions, then the many collisions, and then play around with it and see what you can do, because it'll show you what's going on inside the beaker if you play with it right. Next ETD, I'll explain what's going on using the simulation and all that stuff. And this is my favorite PhET of all time. It's the best one they ever designed, so you should definitely check it out if you can get there. One thing that you might have to find is a different Internet Explorer. It might work with Google. It depends on what your platform is. I can get it to work on school computers, so you can hopefully figure out how to get it there. Sometimes we've had to open it in an Internet Explorer. Other times it works in Chrome. We'll see what format they have this year. It'll be fun, right? So normally we go after the intro to equilibrium lab and we do all that stuff, but the ultimate job would be for you to figure out how the clock reaction shows this property called equilibrium and how that ties into, uphill and downhill battles. Our ultimate goal today was to think about how looking at the molecular structure of a molecule can tell us how much energy is involved in it. And then looking at its delta H could tell you how much energy is available in that fuel source. And then maybe thinking about how we could get that amount of energy from a different process that didn't produce so much CO2. Alchemy. You gots to love it.